All right, in this lecture, we're going to lay down the groundwork necessary for a study of what I'll call complex circuits. Those will be circuits that involve two or more batteries and assorted resistors. We'll begin with a discussion of a thing called signed resistor voltages. I'll illustrate a signed resistor voltage with this diagram. I show a portion of a circuit, just showing one resistor in the circuit. It lies between the points in the circuit labeled A and B. And from our perspective, there is a current traveling from left to right, from A to B. Associated with that current carrying resistor is what we call a voltage, a resistor voltage. It's a signed resistor voltage, meaning that there is a sign, positive or negative, attached to it. There's a rule that we follow in order to determine whether the sign voltage is negative or positive. Here are the two rules. If you imagine an observer traveling through the resistor with the current arrow, in other words, in this case from A to B, in the same direction as the current arrow, then you put a negative sign in front of the product I times R. On the other hand, if your imagined observer is traveling against the current arrow, in other words, from B to A, then the signed voltage is positive I times R. Notice that we're using a symbol V to represent the signed resistor voltages. Try not to confuse the symbol V that we use to represent a signed resistor voltage with the abbreviation of the word volt. They're different things. The second of the two kinds of signed voltages you need to understand in order to work problems involving complex circuits is signed battery voltage. I show a battery, one of perhaps many in a circuit. Between points A and B in the circuit, there is a power supply, a battery, whose EMF is symbolized as E. Again, with the imaginary observer, if you travel through the circuit, through the battery from A to B, traveling from the negative side of the battery to the positive side of the battery, then the signed battery voltage is positive EMF, whatever the EMF is, and it's measured in volts. The signed battery voltage is just whatever is the EMF of the battery. On the other hand, if you imagine an observer traveling from B to A, from the positive terminal down to the negative terminal, then you put a negative sign in front of the battery's EMF. Now, let's look at this simple circuit. One battery, one resistor, and I label 4 different points around this circuit. It's not hard to see that with a 6-volt battery and a total resistance of 3 ohms equivalently, that the current out of the battery is from A to B, and it's 2 amperes. Suppose we travel through this battery or around this circuit, A to B to C, D, and A. So imagine us traveling around the following, we'll call it a loop. A, B, C, D, A, and we're back to where we started. Let's determine the two different signed voltages that we encounter. If we travel from A to B, that's C to D to A. From A to B, we travel from the negative terminal of the battery through to the positive terminal of the battery, and so this rule is invoked. The assigned battery voltage is positive 6 volts, as shown here. Now what about traveling through the resistor? In traveling from A to B, we go through the resistor with the current arrow, in the same direction as the current arrow. In such a case, we invoke the with the current arrow rule and assign a negative sign in the front of the product I times R. And so there's our negative sign, I times R, negative sign. I is 2 amperes, R is 3 ohms, the product is 6 with a negative sign. The final result for the resistor, signed resistor voltage is negative 6 volts. I'm going to point out something that we'll make reference to more than once in the coming work. As we travel all the way around the circuit, ending up at the starting point, in other words, for example, from A to B to C to D to A again, the sum of the signed voltages that we encounter is 0. Check it out. From negative to positive for the battery, it's a positive 6 volts. For the resistor, it's a negative 6 volts. The sum of 6 and negative 6 is 0. It'll always be the case in our coming work that when we imagine an observer traveling around in a complete closed circuit loop, around what we call a loop, then the sum of the signed voltages we encounter will always be 0.